I'm Dr. Ajay Sharma, Department of Electronics and Communication Engineering, James Engineering Management Technical Campus, Knowledge Park 3, Greater Noida. The subject that I teach in this semester for BTech 7 semester students is Optoelectronics and Optical Communication. And the topic that I discuss today in this video lecture is digital receiver performance and sources of errors. Sources of errors means sources of noise. Actually, the performance of any receiver 90% depends upon optical detector as far as optical receiver is concerned. And the performance of any receiver is judged on the basis of that, how correctly the receiver declare 1 and 0 as far as digital optical communication is concerned. So before the decision comes from the receiver has many circuits of amplifiers and filters, and the responsibility of filter is to filter out, to remove the noise components from the received signal, so that not only that, and we have amplifiers also to amplify the signal. So what we do, what this receiver sorry. So what the receiver do in optical communication is to, first of all, we remove the noise contents with the help of filters and amplify the signal power, right? And then what's happened? Signal to noise ratio increased. So when S by N ratio is increased, then there is a better chance that receiver declared a bit correctly. And after that, what we have to compare whatever the output that we have after removing the noise contents and amplify the signal power, signal voltage. Then we have to compare this with the threshold level. Threshold level is already predefined at the receiver by the engineers. So whatever the output that come after filtering or amplification, then this particular voltage level is compared with the threshold. And then receiver is able to determine whether a pulse is available at a photodetector at a given time slot or not. So ideally, whatever the output is, if this output, look at this slide, if this output is greater than threshold voltage, then receiver declare binary 1 is present. And when this voltage output is less than threshold voltage, then receiver declare binary 0 is present. So in that way, the receiver declare 1 and 0. Sometimes this particular voltage, this V out is deviated from its real value, because the reason behind it that there are various types of noises that are generated inside the receiver, and there are also chances of interference from adjacent pulses. So these are some reasons, that's why some deviations that is coming out of average value of V out. Now come to the noise sources in a receiver. Actually, the term noise means a noise signal or a noise power, right? And it is also a signal, but it is unwanted signal. That's why this signal come in the category of noise. So those signals that the engineers don't want to come, then those type of signals become a noise, right? So noise is also a signal, but we don't want that signal. That's why this is a noise. So the term noise describes unwanted components of an electrical signal that tend to disturb the transmission and processing of the signal. So that noise, which is an unwanted signal, if that come, then this particular noise disturb the transmission as well as processing of the signal and makes the receiver to do incorrect decision, right? So we have to first understand these noises. When you understand the noise, then you have, you know, then you are able to follow the procedure to remove the noise. So first of all, we want to understand that the sources of noise that come in the picture as in the noise receiver, so that we are able to remove them. First of all, at the starting, when I say at the starting, when it's a time when the signal from outside, which is a optical signal or a light signal coming from optical fiber. So actually light is composed of many small particles, and the smallest particle of the light is called photon. So there are thousands of photons is there in a light signal, and when they arrive at the arrive at the detector, because the input of the detector is the light signal, or you may say photons. So when therefore the photons, when they arrive at the input of the detector, and when there is an impact of this photon on the active area of the active area of the detector, so their arrivals are random. They are randomly moving. They are randomly moving and have impact on the active area, active region, active plate of the detector. So the random arrival rate of signal photons, light signal photons, produce a noise, and that noise is called short noise or quantum noise. So short or quantum noise comes in the picture in a optical receiver because of the random arrival rate of the photons that is coming from optical fiber. So this is the first stage we see that type of noise in optical receiver, and that noise is called quantum or short noise, right? So this is because of the random arrival rate of a signal photons. Come to the second, it's a dark current. Dark current comes from thermally generated electron hole pairs in the p-n junction. Dark current means in absence of light, because detector is reverse bias. We don't want current because of the external source. So we always do reverse biasing in photodiode. But even then we get a current. Actually this current is because of course there is absence of light, but we get little bit amount of current because of the temperature increase or because of some heating. Electron hole pair, some electrons are free, not because of the photons, but because of the thermally generated. So because of the rise in temperatures. So because of that, there is a little bit out of current flowing in the circuit, and that current will be called as a dark current. So dark current is because this comes in the picture in the absence of light, in the absence of photons, and it's a very very low current. So this is called dark current. Now third category is additional short noise that arises from the statistical nature of the APD process. So thermal noise arises from the random motion of electron in the detector load resistor and in the amplifier electrons. Then come in the category of thermal noise. Thermal noise is because of the resistance, first of all. Thermal noise because of the temperature. So here the thermal noise means when you take the output and we have some load. Because you always take the output through some load, so load have some resistance, and that creates a thermal noise, right? So basically, these are the sources of the noise that come in the scene of optical receiver operation. So first of all, we start with the first stage. These are the photon stream, and each photon have energy of h mu, where h is Planck's constant, mu is the frequency of photon. So these are the photon streams. So in that stage, we have a photon detection quantum noise, or you will say short noise, right? And their fluctuation follow Poisson's distribution. So this is the first stage. We get which noise? We get short noise or quantum noise. Then this is a photo detector, and normally 90% we use avalanche photo detector. So avalanche photo detector has some gain factor M or current gain factor M. So in this stage, in the photo detector itself, there is a dark end in the absence of light, in the absence of the impact of photons, and this is the statistical gain fluctuations for APD, right? Then after that we have this resistor, and through this resistor we have a thermal noise, right? So thermal noise always we take across some resistor, across some load, and load is nothing but it's a resistor. Then we use amplifiers, so amplifier noise also come in the picture. So we start with this and end with this. So these are the sources of noise that creates problem for us in optical receiver. Now come to the calculations of how we calculate these noises so that we get S by M ratio. So we start with quantum noise current, and this bracket IQ square, actually this is the noise power. When you square voltage or when you square current, it becomes power. So this factor also shows the current, and current become a power when you square this term. So basically this term is the quantum noise power because of the quantum noise current. So sigma q square is also denoted with that quantum noise. So this is the quantum noise, and it is equals to 2 q IPBM square FM. So B is the bandwidth, FM is the noise figure. Actually, noise figure is defined as the ratio of signal to noise output upon signal to noise input. It's the ratio of these two quantity. So basically, this FM is equals to m to the power x. So this x have a value between 0 and 1, and that x, this particular value depends on the material that you use to manufacture APD. So now we have a dark current. So this represents dark current noise power, or due to dark current noise, and is equals to 2 q ID. Instead of IP is ID, and this is the dark current. B m square FM, and B bandwidth, M and gain factor, and FM is the noise figure. Then surface dark current, IL is the surface current. Again, this only difference is this IL. B same. And for PIN photodiode, this particular, because M is equals to 1 and FM is equals to 1. So this factor is equal to 1 in PIN. This factor come in the picture when you take avalanche photodiode, right? Now the total photodetector noise current, if you summarize all these three current sources in previous slides. So summation of these IQ, this is the quantum noise source noise, this is the dark current, this is the surface dark current, and if you take the sum of these, this is the total RMS photodetector noise current or power. Look at this. Just add them. Then come to the thermal noise. Thermal noise is IT square. This is thermal noise due to thermal current. And this is 4 kTB upon R. Students also aware with this particular formula in previous classes. Where K is a Boltzmann constant, T is the temperature, B is the bandwidth, R is the load. So RL is the input resistance of amplifier, and KB is equals to Boltzmann's constant equal to 1.38 10 to the minus 2 joule per Kelvin is Boltzmann. It's a constant. And here T is the temperature in Kelvin. Now, when you have a signal power, when you have a noise power, what you have to do? Take the ratio, so you get the S by N ratio. So, having obtained the signal to total noise, the input signal to noise ratio can be written as this. So, in denominator is total, you just add all the noise sources, and at numerator we have a signal power, and this signal power actually the photon current, and if you square the photon current, it becomes photon power, and if you multiply with the current gain factor, then become a total photon current, or you measure total photon power due to photon current IP, and take the ratio, then this becomes S by N, right? So this is this expression just have, finally S by N ratio that you get is this. So the important thing is this denominator that is coming after you calculate all the noise sources. And this is very simple. Signal power is simple. Signal power is because of the totally photon current, because of the photons. And if you 90% you consider APD, avalanche photodiode, you always multiply with the current gain. Thank you very much.